We've talked in this unit so far about the types of charges that we can have, positive and negative, and how to charge objects either by conduction or induction. We've talked about how to calculate forces and fields caused by charges. Today what I want to do is talk about what happens to the individual charges either in or on a conductor. Now these charges might come about as a result of rubbing two objects together. Maybe you have more electrons because you've rubbed two objects together and you've charged by friction, or maybe there's been a lightning strike. The bottom line is you have more electrons than protons on an object, or more protons than electrons on an object. The goal here, when you have a conductor with excess charge, the goal is always to reach a state of static equilibrium. That means that all of these charges, these excess charges, repelling each other. Remember, if you have two electrons, they'll repel each other. If you have three electrons, they'll repel each other. If you have 1,000 electrons, they'll repel each other. If you have a point of static equilibrium, these forces of repulsion that act between all of these excess charges end up balancing. And as a result of that, these charges are at rest. So they move around like crazy as these forces of repulsion are trying to balance each other. And then at some point, they do balance each other, and these excess charges become at rest. That's static equilibrium. Now this occurs in conductors because the charges are a lot more free to move about. You don't see this so much in non-conductors or in insulators. I want to take a look at a few specific shapes and what the state of static equilibrium will look like in these different shapes. First one I want to take a look at is a solid conducting sphere. This is like a marble, except it's made out of a conductor. Let's say that on this solid conducting sphere we've got 3 excess electrons. Maybe we've got 1,000,000 protons, but it would mean that we have 1,000,003 electrons. Now, in the end here, if we were to have 1,000 excess electrons, we would go through the same process and we would observe the same thing. The analysis and the diagrams that we draw would just be more complicated, that's all, but it would work the same way. Take a look at diagram A here. Diagram A shows 3 excess electrons that are somewhere inside this solid conducting sphere. I'm going to label these charges charge 1, charge 2, and charge 3. And I want to look specifically at charge 1 right now. Charge 1 is repelled by 2 other charges, charge 2 and charge 3. The force of repulsion caused by number 2 is going to go this way. We'll call that F21, the force of charge 2 on charge 1. It's a repulsive force. It pushes away down and to the left. Now there's also a repulsive force caused by number 3. 3 pushes 1 this way. We'll call that F31. It's a repulsive force that causes charge number 1 to move to the left. Now, as a result of both of those repulsive forces, we end up with a net force acting on charge 1 that's somewhere down and to the left. It's a combination of F31 and F21. Now, we get a similar phenomenon taking place with charge 2 and charge 3 as well. Charge 2 is repelled by charge 1. We'll call that F12. Charge 2 is repelled by charge 3. We'll call that F32. And as a result of both of those repulsive forces, there's a net force acting on charge 2 this way. You'd see the same thing with charge 3. We just won't draw it. Now, as a result of these green forces, these net forces acting on charges 1 and charge 2, all of these charges end up being pushed outwards. So they get pushed to the outside, the outer surface of this conductor. In fact, that's what happens when you have a solid conducting sphere with excess charges. The charges will, A, always be pushed to the outside, the outer surface, and B, if you notice the distribution here, they will always be evenly distributed on the outer surface. So remember that. If you have a solid conducting sphere with excess charge, then you're going to find that these excess charges go A, to the outer surface, and B, they'll be evenly distributed. Always, every single time. Now let's take a look at another shape. This is a solid, flat, conducting plate. This is a uniform surface. It's flat, just like this solid conducting sphere was a uniform, round surface. No crazy edges or or spikes or anything like that to it. I'm going to label these 3 excess charges in this solid flat conducting plate, just the same as I did last time, charge 1, charge 2, and charge 3. I want to focus on charge 2 here. Okay, charge 1 and charge 3 are there, but I want to focus on charge 2 here. Charge 2 experiences, as a result of these 2 excess charges, these other 2 excess charges, charges 1 and 3, experiences 2 forces. There's the force of 1 on 2. There's the force of 3 on 2. 1 repels 2 to the right, 3 repels 2 to the left. Now, the force of 1 on 2 is a bigger force than 3 on 2 because 3 is further away from charge 2 than charge 1 is. So as a result of these 2 charges being closer than these 2 charges, you're going to find that F12 is a bigger force. Now, as a result of F12 being a bigger force, this charge number 2 is going to experience a net force to the right. That means it's going to move to the right. But as it moves to the right, F12 will decrease as the charge gets further away from number 1, and F32 will increase. There will come a point when the force of 3 on 2 and the force of 1 on 2 end up being equal to each other. That's your point of static equilibrium. The forces are balanced. These charges are now going to remain at rest. Now, take a look at the distribution again. You'll notice A, these charges are once again on the outer surface, and B, these charges are evenly distributed. So far we've dealt with 2 shapes, 2 nice, uniform, smooth shapes, a solid conducting sphere and a solid flat conducting plate. In both cases, the excess charges went A to the outer surface, and B became evenly distributed on that outer surface. Now we're going to change it up a little bit. This time we're going to have an irregularly shaped solid conducting object. So it's kind of a pointy object. I want you to take a look at the first diagram here, diagram A. I want to look at specifically 3 charges. We'll label them charge 1, charge 2, and charge 3. We could look at charge 4 as well, but in the end, we're going to see what we want to see simply by looking at these 3 charges. Now, there's a repulsive force of one of these acting on all of the other ones, but specifically, I want to look at charge number 2 again. Charge number 2 is pushed away from charge number 1. We'll call that F12. There's a repulsion force that causes charge number 2 to be pushed towards the tip of this irregular shaped object. Now, it's also pushed away by number 3, or repelled by charge number 3. We'll call that F32. That pushes it kind of up and to the left. I want to break charge 32, however, down into 2 components. We'll call this the y component of F32, and we'll call this the x component of F32. The y component of F32 pushes charge 2 to the outer surface if it's not already there. So once again, our charges, our excess charges, go to the outer surface. Now, F12 and the x component of F32 kind of work in this situation where they're acting against each other. 1,2 is trying to push it out towards the tip, and the x component of 3,2 is pulling it back away from the tip. Which one wins? Well, F12 is a bigger force than the x component of 3,2. That means charge number 2 is going to be pushed away from charge number 1 and go towards the tip of this irregularly shaped object. Now, as it goes further away from charge 1, closer to the tip, F12 is going to decrease. And at some point, Fx and F12 will balance each other. That's when it's in static equilibrium. But that's not going to occur in the same situation it did when we had a uniformly shaped object. That's going to occur when we have, well, our object or our charges are at the outer surface of the material, but they're more concentrated towards the tip. They're not evenly distributed like they were on the solid conducting sphere or the solid flat conducting plate. So, here's the summary so far. If we have a uniformly shaped object, whether it be spherical or whether it be a solid flat conducting plate, we will always have the charges go to the outer surface, and they will always be evenly distributed. If we have an irregularly shaped object or a pointy object, the excess charges will still go to the outer surface, but this time they will be more concentrated at the tip. When you walk across carpet and you develop a charge because of friction as your feet rub across the carpet, and you go to shock somebody, you don't shock somebody with the side of your arm or your hip. You touch them with your finger. And the reason you touch them with your finger is because the charges are more concentrated on your fingertip than they would be on something that's more uniform, like your hip or the side of your arm or your leg. Lastly, I want to look at a hollow conducting object, and I want to look at this a little bit differently than the other ones. We know what's going to happen to these charges. Same thing as would happen in a solid conducting sphere. The charges are going to go to the outer surface, and they're going to be evenly distributed. This is a uniform surface, so we're going to get the same effect as we got in the solid conducting sphere. But what I want to look at a little bit closer here is the electric field. The electric field, you can see in diagram B here, the electric field caused by each of these excess charges on the outer surface evenly distributed points toward the negative. We expect that, right? Charges that are positive cause a field that points away from it. Charges that are negative cause a field that points toward it. But I want to look at the field inside this conductor. The field inside this conductor caused by this charge points this way. Then we have a field pointing towards this charge pointing towards it this way. And then we have another charge down here that has a field pointing towards it this way. If we did a vector analysis of all of those electric fields inside this hollow conducting sphere, we would find that the net field is 0. That's a big deal. That means that every time we have a conductor that has excess charges, the net field, the net electric field anywhere inside that conductor is 0. That means that anything inside can't be affected by the electric charge on the outside. That's why when your car gets struck by lightning, everybody says a car is a safe place to be in a lightning storm. It is. But the misconception is that it's a safe place to be in a lightning storm because of the rubber tires. It insulates it from the ground. If the electrons can make it from the cloud to the ground, or from the cloud to your car, they can make it from the car to the ground through the rubber tires. It's not the rubber tires that makes the car a safe place to be at all. Rather, it's the fact that your car is a conductor. When it develops excess charge as a result of a lightning strike, the charges stay on the outside. The electric field inside the car, as a result of all of those charges on the outside, cancel out. The net electric field inside the car is 0, which means you can't be affected by that electric field, which means you're safe inside your car. We call that a Faraday cage. When you have a conductor with excess charge caused by whatever, the net electric field inside is 0.